Okay, so we're here for the 6th lecture on the proof complexity as a computational lens course. We're in the middle of a lower bound proof for k-clique formulas. So what are we doing? We're doing an average case n to the big omega of k lower bound. Just to be sure. For k-clique formulas, we'll get in a second to we'll do a recap of where we are. We would love to do this for general resolution, fully unrestricted resolution, but we are not able to do this. So we'll do it for regular resolution. What do we mean by average case? We mean that the graph is sampled uniformly at random from the Erdős Rényi graph distribution with n vertices, and every edge is included with probability n to the -2 over k minus 1, almost. This would be the critical density for k-cliques to emerge. So at this density, we would expect k-cliques to emerge. So we'll tweak it ever so slightly by multiplying by an eta for some eta constant that is larger than 1. So now we know that this distribution asymptotically almost surely will not contain k-cliques. So it makes sense for resolution to refute the existence of k-cliques, but it will be a hard graph family because there will be tons of cliques of size big omega of k. That's the intuition. So what is regular resolution? Just to recap. So we're going to have a few minutes of recap where we are in the proof. So let me start by doing that. Regular resolution, look at the proof tag. And a proof is regular if along any path in the proof tag, in the resolution refutation tag, every variable is resolved over at most once. And we talked about last time that this is a very natural restriction. I would make the argument that most proofs you will ever see in your life, most resolution proofs, to the extent that you will see resolution proofs at all, will be regular. But it is a restriction. We know that regular resolution is exponentially weaker than unrestricted resolution. So we talked about last time that regular resolution is actually the same as read-once branching programs. We did not prove this equivalence. We don't need the full equivalence. We just need that from a regular resolution, we clearly get a read-once branching program. So what does a read-once branching program? It's kind of a decision tree, except it's a decision DAG, if you will. Every node is querying a variable, and then depending on whether the value of the variable is true or false, you take the one edge or the zero edge out of the node. And then when you hit the sink, that sink should be labeled by a clause. Now, any truth value assignment defines a path through your branching program. The branching program solves the falsified clause search problem for the CNF formula F if any assignment defines a path that leads to a sink that is labeled by a clause that is falsified by the assignment in question. And the read-once condition is that along any path, any variable is queried at most once. And if you just take a regular resolution refutation and you invert all the arrows, then you have a read-once branching program. Okay, so we're going to phrase our proof in the language of read-once branching programs. We're going to do the formula we're looking at is we have clique axioms that say that every clique index I corresponds to some vertex V. So some vertex V is the ith clique member. This is for all i's in K. If we're talking about the k-clique formula, we have edge axioms that say that, well, if UV is not an edge, then it cannot be the case that vertices U and V are both in the clique. Then we have functionality axioms that say that that the ith clique member is uniquely defined. So it's not the case that two different vertices U and V are the same clique member I. And then one type of axioms that I'll just write them down for completeness because the lower bound works for them, but we will be a bit lazy and we will not consider these axioms. The ordering axioms say that, well, if U comes before V in some ordering of the vertices, and if UV is an edge, then I still don't allow U to be the ith clique member and V to be the jth clique member if I is larger than J. These are ordering axioms. It's some kind of symmetry breaking axioms. What we're going to talk about today actually works for the clique formula with ordering axioms, but just for simplicity of exposition, we're going to ignore this. We're not going to have these axioms because most of the proof is interesting even without this. Let's see, is there anything else? Yeah, so what are we going to prove? We're going to prove that the theorem we're looking for is, and I'm not stating this, but they're in the paper by Atserias, Bonacina, Susanna de Rezende, Lauria, myself, and Alexander Razborov. The statement is a little bit more general, but what we're going to do today is to just say that for constants, so you can have them not to be constants and compute exactly how the lower bound scales. But let's for now fix epsilon to be any positive constants. As we said above, eta is larger than 1. Let the k, which is the size of cliques we care about, be at most n to the 1/4 minus epsilon, so asymptotically smaller than the 4th root of n. Then the k-clique formula, for a randomly sampled G, again from Erdős Rényi distribution, n vertices, and as we said, the edge density minus 2 eta, oops, let's see if I can do the eta correctly. Here it comes, over k minus 1. Such k-clique formulas require regular resolution refutations of length n to the big omega of k. I don't know how the font size is, if I'm getting a bit on the small side or if this is readable. So this is what we want to prove. An n to the k, average case lower bound, everything is nice except, again, we're getting this only for regular resolution. So as we're doing the proof today, the main challenge would be to do exactly the same thing, but for fully general resolution. We have a graph that we're going to talk about G. We're going to have vertices in this graph be U and V and W.
Sorry, the chat is saying it's a bit hard to read.
Okay, so we'll
maybe
increase the font size a little bit.
Yeah.
Let me say that the graph G are going to have vertices U, V, W, things like this. When we talk about the branching program, it's going to have nodes, and I'll refer to them as A, B, C, because there are lots of graphs around. And so, I mean, the branching program is also a graph, but I'll refer to the branching program as having nodes, A, B, C. And the graph for which we're refuting the existence of a k-clique will have vertices U, V, W. Okay, let's review some key technical definitions. So what did we do last time? Actually, we set up a beautiful proof approach, and the only problem was that it crashed and burned. But it turns out that we should really follow this approach. We just need to fix our definitions and make them a little bit smarter, and then it's going to work. And that's what we're trying to do today. And since this proof is a little bit, well, at least I think it's somewhat technically complicated, I think it's worth recapping the main definitions to just check that we're on the same page. The first key observation is now A is any node in the branching program. Beta of I is the variable assignments that are common for all source paths, all source paths, so paths starting at the source of the branching program and ending at A. So this means that basically here we have the starting node, the end node of the regular resolution refutation, if you wish, the start node of the branching program. Somewhere here is A. There are many different ways potentially to get to A. And we observe that since the branching program is read once, any path in the whole branching program corresponds to partial truth value summit. And that's a key observation that we'll use over and over again. However you traverse the branching program, the edges that you take will describe a truth value summit. There's no way to walk along a path in a conflicting way because you never query a variable twice. This is like a key technical condition. This means that every path from the start node to A defines a truth value assignment, and basically taking the intersection of all of these is beta of A. This is, at this point, beta of A is sort of what the branching program remembers when it has reached A. It could also, there could be assignments that it does not remember. Maybe it asked about some unique variable X over here that it didn't ask about at some other path. But then because of the read once property, it cannot ask for X again. So for all practical purposes, the value of X is just forgotten. So let's write that down. So X is forgotten at the branching program node A if two things hold. There exists some path, there exists a source path alpha to A that sets X. So that there is some path along which X is queried and hence gets a value, but X is not in the domain of beta of A. Then we say that X is forgotten. And the first observation, we're going to recap a number of observations that we had. The first observation is that, well, if X is forgotten at some node A, and if there is a path from A to some other branching program node B, then X is forgotten at B also.
In the definition, you said X is not in the domain of beta, right?
Thank you. Yeah, so X is forgotten if it was queried along some path, but not along some other path, therefore it's not in the intersection of all paths, then it is forgotten. Thanks. And the fact is that it means that if I have this property already here, and then I can continue to B, then the same, just concatenating these paths with the path from A to B shows that by the definition of being forgotten, it's still forgotten. But basically, the way to think about this is if you queried a variable that's along some path and then you forgot about it, then you're screwed. You can never, ever learn anything about this variable again. And so in particular, we'll say that an index I, not just a variable, but an index I is forgotten at A if some variable xvi is forgotten. So if there is some variable v for which I've asked along some path whether v was the ith clique member or not, and I received an answer, but then I forgot about it, then for all practical purposes, I've forgotten everything about this index. And in particular, if this happens from a path, whatever the branching program will do after the node A, it will not be able to end in a sync node that violates the ith clique axiom, because it has forgotten a variable, and if it ends in a sync, then the assignment, all assignments reaching that sync must violate that axiom. But clearly, we will never violate any axiom containing XVI positively if it's forgotten. Okay. We also say that the source path rules out the index I a source path rules out index I at the sync B if B is labeled by the sync axiom for clique member clique member I, sorry. So a big OR for all vertices V over XVI. So the branching program rules out index I if it actually it's given, if that path ends in a sync showing that the assignment picked up along this path falsifies this sync axiom. And now the next key observation that we had is that, and this is really just putting together our observations, if a source path alpha rules out index I at B, then I is not forgotten at B. Because any path ending at the node B that is labeled by the sync axiom must set all variables in the sync axiom to false. In particular, none of them could have been forgotten. Are we happy so far? Okay, so then our idea was in our lower bound that we wanted to do basically a bottleneck counting argument. We wanted to define a random distribution, fix a branching program solving the clique formula, define a random distribution, show that it has to pass through a node. The first idea that we had is from the lower bounds we did for pigeonhole principle and Satan formulas, where the bottleneck counting is basically show that we have to pass through a node that somehow contains lots of information. Then show that for any random walk passing through a fixed such informative node is very unlikely. Deduce that there must be many such nodes. Here we're going to have a twist. We're actually going to define informative pairs, which are two waypoints on a path in between which lots of exciting stuff happens. But we need to define, let's recall what the random distribution D was. So let's see if I can fit the random distribution fancy style D over path. So for now, we're fixing a branching program. And the random distribution is constructed, we start in the start node, and then we just construct the branching program. We make a random choice in each new node, and then just construct the path inductively. So suppose we're currently in A. Suppose that the current node is A. Then we do the following. First, we check, would it be obviously stupid? And suppose that A queries, it queries XVI, say. Okay. Well, if what the branching program knows at A, combined with saying yes, that indeed vertex V is the ith clique numbers. If this causes an immediate contradiction, if this falsifies edge or functionality axiom, then we say that then we set XVI to 0, meaning that we take the 0 edge out of A. Second, if the index I is forgotten at A, then we also set XVI to 0. Because we kind of know at this point it's not so interesting. Whatever the branching program is up to, it will not end by refuting the ith clique index. So it's sort of, it's safe for us to set XVI to 0, and it will have to make the branching program work harder on other parts of the graph. I'll refer to A and B as forced choices. And then we had our free choice, which was, well, if neither A nor B applies, then we could actually set XVI either to true or false, and we'll do so randomly. We'll set XVI, otherwise we set XVI to 1 with probability n to the minus delta for some delta that we'll fix later. Okay. So otherwise, if neither A or B applies, we flip a coin and set XVI to 1 with probability n to the minus delta and 0 otherwise. And this is our random distribution. This we had already last time, and we don't need to fix this.
Is there a reason why we want to be biased?
Like, why don't we do just a random 50-50 coin flip? The reason is that what would typically happen is the branching program, then it would be very easy, even just for a single vertex V, right? Suppose I would just ask whether this vertex V is clique index 1, 2, 3, 4, 5, then with overwhelming probability, I would make any vertex be in the clique. And in general, there's an asymmetry here. We had something similar when we proved pigeonhole principal lower bounds. There's a clear asymmetry between 0 and 1. 0 is the safe choice. It doesn't reveal too much. 1 reveals almost everything, because once you have a 1, you know that the branching program will just work on the residual graph that is the neighborhood of this vertex. And you can expect this neighborhood to shrink dramatically for every new clique member that you pick up. So you want to be very, very careful with setting vertices, variables to 1. But still, I mean, if I set everything to 0, then it also becomes boring. So there's in fact, getting this delta right is part of the problem. Okay, so now we also argued last time, I'm still in recap mode, that look at an alpha that is sampled according to this distribution. Clearly, alpha rules out some clique index. And today I'll try to be consistent and say that this clique index is I star to distinguish it. When we just see I, it will be an index that floats around, and I star will tend to be the clique index that the alpha that we're talking about rules out. So how do we know that any alpha ends in a path that rules out the clique index? Well, because as soon as you could falsify an edge or functionality axiom, you just set the variable to false. Right? So whenever you risk falsifying one of these two guys, you just set the variable query to false. So you can never violate, by construction, you will never violate, maybe I should let, so this is the clique axioms. This is the edge axioms. These are the edge axioms, and these are the functionality axioms. So by construction, I will never violate these. So I will hit a sink that violates a clique axiom. For the same reason, and using that we know something about the graph, in particular, we know that the graph does not contain a k-clique, and therefore we know that alpha sets at most k variables x, v, I to true. Okay, and now we're actually, this is roughly how far we got last time. Last time we had all this set up, and then we said the following, that we defined a useful pair of branching program nodes A, B. This is a B, for those of you who wondered. That's how I write my B's. A useful pair A, B on an alpha that rules out I star. Our idea was that's a segment where many variables x, u, I star are set to 0. And we know that looking at alpha, its end goal is to rule out I star. And then we somehow just chop the path alpha up into segments, and we say that a segment is good or useful, it makes progress, if it makes progress towards its end goal. It wants to rule out, it wants to pick up x, u, I star equals 0 for all vertices u. And if it does so for a significant fraction during this segment, then let's say that something good happened between A and B. This was a useful segment. So AB is a useful pair. Okay.
Observation 3 should be k minus 1.
Well, in particular, yes, which means that k is also true. It's an at most.
Is it like this?
Yeah. So, but you're absolutely right. But that means then you would have to force me to type -1 everywhere, and I don't want to do that. So I'm going to stick with k. But it's a good point.
It's always the same I. It's a
no. These are different variables I.
Oh, different variables.
Yeah. Yeah, because this is the I star, this is a special one, and this is any I that is just floating around. So this is like, you know, xv1 I1, xv2 I2, oops, etc. At most k of those guys are set to true, or in fact, at most k minus 1, but who cares? We're not going to be that precise. And k is less typing than k minus 1. So now we defined a useful pair, and then we argued basically by just an averaging argument that every alpha goes through a useful pair. Some useful pair AB. And this was almost immediate. And then what we wanted to show was that, well, suppose we fix A and B, and over the random, so now look at a fixed useful pair, sample the path randomly, and let's look at the probability that alpha goes through not a sum AB, but this fixed AB. Okay? And we wanted to argue that this was basically something like n to the minus k. Okay? If we would have been successful, then we would have been done, because with probability 1, it goes through some pair. For a branching program with s nodes, how many pairs can we have? Well, at most s squared. But if for any pair, any concrete pair, the probability of hitting it at most n to the minus k, then the size of the branching program would be n to the k square root of this, would be n to the k over 2. And we would be happy with this. And the only problem was that the proof crashed at this point. That's where we are. Questions? Because now we'll start to fix the proof. We need some more refined definitions, and then we're going to do a lower bound that actually works. Except there are going to be some hideous calculations, and I'm going to spare you those. And just try to hand wave. I maybe say something about it, but I talked to Susanna about it this morning, and she also agreed that we shouldn't really torture you with calculations. Is it? So questions up to this point, because this is like a recap of what we did last time. Okay, we're happy? Okay, let's just make sure we're absolutely on the same page. You've seen this notation before, but now we're in the graph G, right? Because V is a vertex. So let's just make absolutely sure that we agree with the neighbor of V is, that is any U such that UV is an edge in the graph. Yes? These are the neighbors of V. Let me define common neighbors of R. I'll give n a hat to denote common neighbors. If R is a set of vertices, then the common neighbors of R are, well, the common neighbors. Okay? So I just take the intersection and take all the neighbors. Why is this an interesting set to think about? Well, suppose that R is a clique that the branching program has figured out. Then without loss of generality, we're only going to play in this set. And so in particular, this had better be somewhat large, or otherwise we're screwed. In particular, but we're going to need more than that. We're actually going to need, we are somehow going to be interested in a particular set W, and we are going to be interested in the common neighbors of R inside W. So n hat sub W of R is just going to be n hat of R intersection W. Let's hope that I got this right. So we're going to use this notation heavily. And basically, getting ahead of ourselves a little bit, you should think of, let's think of the way, like, how should you think about this definition? Think of R as being something that the branching program has picked up so far, maybe the ones for the branching program so far, so the subclique. And let's think of this as a set of zeros that the branching program manages to pick up. We're kind of interested in how hard was it to figure out that all of these guys in W were zero? Well, it depends on the size of this set, right? Because if this set was basically nothingness, then there were a lot of forced zeros, and the branching program didn't need to do anything. But if this was a fairly large set, then a lot of the time we can hope that we were in KC and we were doing coin flips. Am I making sense? Okay, so this motivates the following definition, and this is absolutely some key definition now. Let's say that W, a subset of vertices in the graph in V, it's Q neighbor dense for R, also in V. If looking at the common neighbors of R in V, this set has size at most Q. Again, this means so a set is W is Q neighbor dense. If suppose that R is my clique, how many ways could I extend this clique with at most at least one more vertex in W? I have at least Q choices. Okay. And now let's say that W is RQ neighbor dense. So basically this says that W is a good set if we picked up R to be our clique. Now let's look at sets that are like universally good. Okay. W is universally good from our point of view when we want to prove lower bounds. It's RQ neighbor dense if for all R's of size at most lowercase r, W is Q neighbor dense. Q neighbor dense for R. Okay, this would be an amazing property. This would mean, hang on for a second, let me just say that this means if I'm looking at this set, then regardless of what clique I've picked up so far, as long as it's not larger than size lowercase r, I can extend it in many different ways.
Yeah, I just wanted to re-ask about the intuition you gave for Q neighbor dense. I didn't get that. I'm sorry.
A set is Q neighbor dense. You should think of, I mean, this is not going to be the case when we get to the proof, but you should think of R as being the candidate clique that the branching program has figured out.
Okay.
Okay. Then a set is Q neighbor dense if now the branching program, for some reason, the branching program starts hitting the W set hard.
Okay.
Okay. And now we can be in two settings. What broke down in our proof last time, it turned out that W was a very easy set to get zeros for. And also this was, remember we did the regular resolution upper bound also for K, complete K minus 1 partite graphs. Then we figured out that there were like huge sets where zeros were just coming completely for free. And those sets W we don't like, they're very dangerous for us. W is not such a set if it's Q neighbor dense, because then there are at least Q options for how I could extend the clique with one more vertex.
Okay. And
so for at least Q of these vertices, like when I'm doing my random walk, I'm actually going to have to flip a coin.
So I assume that in the multiplied graph that we saw last time for the upper bound, I assume that those sets are not in, you cannot find them easily.
That's a good question. That is,
Because of
this is not yet what breaks. We're going to need to work a little bit harder on this.
Okay.
Because we need things to be RQ. Basically, okay, the intuition that I want you to keep so far. Suppose that I promised you that for really large parameters R and Q, a random graph is so amazing that any W is RQ dense. Then basically we would run the proof from last time and be home. Okay? The only problem is that this is not true. And the reason for this is kind of, well, a random graph in this setting is actually somewhat sparse. Like it is true that once you pick up a 1, then you do get lots of zeros. So this is not quite going to be true. But the point is that depending on which one you pick up, you're going to get very, very different zeros. So a particular one will be dangerous for one W, namely the non-neighborhood of that particular vertex. But like you could expect W to be good for, if I just suppose that I fix a set W. Okay, let's do the following thought experiment. Let's fix a set W that is somewhat large. And now just pick a random vertex V in the graph and say this is in the clique. What would we expect to happen? Well, if this vertex V was not a neighbor of many guys in W, then obviously now all of W, all the zeros come for free. And this will happen sometime. I mean, if there will be some V's for which W is completely outside of the neighbors of V, right? So there will definitely be bad V's for W. But if it's a random graph, this should somehow be rare. So like for typical W, they should kind of have this property for fairly good parameters. And now we just need to like, wait, but what does this mean? Okay, and now comes the absolutely crucial definition. So we're going to say we do want W to be RQ neighbor dense. So we want it to be good for most R's. We're going to say that we're happy. We can't ask W to be good for all R's of this size. Because again, if I pick the V that is just doesn't have any common neighbors with W, then that's going to be bad. Okay. But like for most R's, in a random graph, I would expect most W's are good for most R's. So let me relax the definition a bit and say that I'm like mostly neighbor dense. Okay. So here goes. And now this is like I tried to motivate things, but here comes the technical definition. I'm just going to hit you with it because there's no sugarcoating it at this point. So here we go. 4 parameters. So a set W is R prime R, Q prime S. And think of R prime and Q prime as kind of being these parameters. It's mostly neighbor dense. If it fails to be neighbor dense, there's a very good explanation. Okay. If there exists a subset of vertices S, which is not too large, how large? This parameter S. Okay. Such that for every R of size at most R prime, if R is such a set for which W is not Q prime neighbor dense. Okay. So this is a bad scenario. We have W, and there are some R's. We know they have to exist. There will be some bad R's for which W is not neighbor dense. But they're concentrated around S. Okay? Namely, R intersection S has size at least R. So then we say this is sort of the best we can hope for. Maybe W is not perfectly neighbor dense, but it is neighbor dense except for a not too large bad set. Okay. And now, let's see if we can fit the final key definition. Okay, so what definitions do we have so far? We have that a vertex is Q neighbor dense for R if it has at least, if R has Q neighbors, common neighbors in all of W. W is RQ neighbor dense if this holds like for all R. It's mostly neighbor dense if it's RQ neighbor dense for all R except if R has a large intersection with S. Okay. Now we say that the graph G is, let's say that the graph is clique dense. Except I'm going to have to use some parameters, K, T, S, and epsilon. Talk about them in a second. A graph is clique dense for some K, which is, think of that as that's the clique size that we're shooting for. So K is a natural number. T, S, and epsilon are positive real numbers. Let's pick T should be at least 1, but not larger than K. Okay. A graph is clique dense if I can find parameters R and Q which are real numbers. R is at least 4K over T squared, such that, and now let's try to like ignore all these parameters and look at the two key conditions that we need. The two key conditions. The whole graph, all of V, is so you would expect that, so sort of what we want to hold and what we should expect to hold is if you start out with the whole graph, all of V, then for a random graph, actually just fixing a not too large candidate set of vertices, I don't even care if that's a clique set or not. So I'm going very worst case here. Then I would expect that such a set, like if there's supposed to be any hope, then for any small clique, it should be possible to extend it in the whole graph in many ways. Note that this is all of V. In fact, I'm going to ask for RQ neighbor density. I'm going to ask for more. I'm going to scale it up by parameter T. Note that if this doesn't hold, then we're like completely screwed in some sense. Like what I'm saying is that I'll talk about how to set these parameters in a second. I realize I maybe should have said it. But basically the whole graph, a random graph, if I just fix for any small set of vertices, I say suppose that this is a clique or it isn't, I don't care. Then they still, any such small set has many, many neighbors in their common neighborhood. If that doesn't hold, then we're not going to be able to prove a lower bound at all. But this is not going to be enough. We will need more. We will need that every, suppose that I have an RQ neighbor dense set W. So this is a set W that is fairly neighbor dense, not this neighbor dense. Note that T is larger than 1, but it's somewhat neighbor dense. I would love to scale it up to better parameters because that is what we need for our proof to work. Okay? It would be wonderful to somehow get T's here, but that's not going to be true. Okay? But I claim that anything that has density with these parameters will be mostly neighbor dense for much better parameters. Okay. How good? Well, it's going to be TR R Q prime S mostly neighbor dense. For Q prime is going to be 3 times epsilon times K times S to the 1 plus epsilon times log S. We don't, okay, let's talk a little bit about, okay, so basically what I'm going to claim now, let me talk a little bit about this definition, and let me talk a little bit about parameters, and then let me talk a little bit about what's going to happen in the group. So basically, the spoiler alert is we're going to prove that any graph that has this amazing property, for such a graph, we can make our lower bound approach to work. Okay, and now what should we think about in terms of parameters? You should think of R and R prime as being scaling with K. It should be clear that R prime is greater or equal to R. We're going to be interested in having Q prime to be polynomial in n, so n to the gamma prime for some gamma prime. We're going to pick S also to be polynomial n to the gamma. And we're going to have that 1 is much, much, much larger than gamma prime, which in turn is much, much, much larger than gamma, but everything is positive. Okay. And basically, okay, we'll do some of the calculations later, but basically this is set up so that now we can hope we are going to define a useful pair now to be such that because of neighbor denseness, in order to make progress along a useful segment and set lots of zeros, lots of them will have to be free coin flips. And then the calculation we wanted to do last time will work. Except there's going to be one explanation when this fails, and that is when we have picked up a clique in the set S. But the set S is fairly small. So we have to be very precise about, we don't have many chances to pick up ones in S. And picking up a 1 is also fairly unlikely. So we're going to have a case analysis that, okay, how did the branching program get many zeros during a useful stretch? One or two things will have to happen. Either it hit this amazing set S, that once you hit S and your candidate clique contains vertices in S, then you got lots of zeros. Okay, that can happen, but S is small, so that's unlikely. Like if the branching program flips ones for S, then we're screwed. But S is small, so you don't get many chances to do that. And if you don't pick up ones in S, then you're kind of neighbor dense for any clique candidate. And then you're going to have a lot of free coin flips. Granted, getting 0 is likely for a coin flip, but getting polynomially many zeros, that's not going to be likely. Is this making some sense? Okay, I don't know. I mean, let's maybe we could just. The question is whether we should. Okay, we should take a break. So let me write down the 2 theorems that we need in order to just be done, and then we'll do one of them. The other one we won't. The first theorem is just going to be that. Okay, in my notes, this is theorem 7. Well, it basically says that with parameters set as before, suppose that we sample with a random graph with the right edge density. Then, with probability 1 minus exponential in the minus the square root of n, G is k-t-s epsilon clique-dense for the right parameters. Namely, we're going to set t to be something like 64 eta over epsilon. We're going to set s to be n over eta square root. Okay. In particular, s is not going to be too large. This is basically saying if I sample a random graph, then it will have this magic property. Okay. How will you do this? Well, just sample a random graph and then do the standard calculations to get that the graph is all of the vertex set is neighbor dense. And then basically to do 2, you're just gonna pick up all counterexamples you can find. You're going to let S be the union of all the counterexamples, and then you're going to argue that S is not too large. These are like at least, well, 3 dense pages of calculations. I was not planning on do this. I could not do this. I have not prepared this. I will not do this. There is a paper doing this. And in fact, if you want to get the result also with the ordering axioms, then you have to tweak the parameters even more and like define a slightly different definition here and work a little bit harder. Okay. So let's just suppose that, proof calculations. Plus some, again, you have to think about the magic thing is how to find this dangerous set S, and this is a little bit interesting. But then you're just doing a lot of like bounding stuff and concentration of measure and what have you. So now suppose that any graph G is k, t, s, epsilon clique-dense. Okay, suppose this holds. Then the regular resolution refutation length for k-clique formulas for the k-clique formula over G is going to be, okay, if we want the full statement, 1 over square root of 2 times s raised to the power of epsilon times k over t squared. And the point with this is just that if you look at this is big omega of k, and s is like some n to the delta. So all of this is n to the big omega of k. So if we can get theorem 8, then we're golden. And I was planning to actually, okay, theorem 7 is calculations. Theorem 8 is not too bad. It's going to be the proof we tried to do before, but we need to be more careful. So I was planning for us to have a break now, and then I'll try to do as much of theorem 8 as we can stomach. And then I would like towards the end, if I'm going to skip something of theorem 8, then that's maybe because I would love to spend a few minutes at the end to talk about the numerous open problems that are connected to this. They're like a rich collection of open problems. The most obvious one is to take this theorem and remove the word regular, but there are many other challenges also related to this. I think this is a good place for a break. Any questions before we take a break? Yes, sorry.
It's kind of the same question. So I assume now that you've said this definition of clique-dense, I assume that the multi-partite graph is not KTS epsilon clique-dense.
Absolutely right.
Yeah. Okay.
Yes. Yes.
And that's where we are using that.
Yeah. So and this I wasn't planning to talk about this, but this is an excellent question. Say like this definition, this property should fail miserably for complete K-1 partite graphs.
Okay. Okay. Thank you very much.
And it does. And if you look at the journal version of this paper, I think we even wrote down exactly how it fits. And I think, okay, you need to work a little bit harder than this, but notice that when you could get many, many zeros, what happened that once we picked up any vertex, like we looked for the kth clique member and we found it in block VI.
Yeah.
Okay. Then we said, aha, I have one here, and since there are no edges within this block, then I just zeroed out tons of other variables, like all xvj for j strictly smaller than I, and for all other v's in this block, I ruled out tons of vertices.
Yeah.
Okay, and I could rule out the same vertices regardless of which v in the block I picked up.
Oh, yeah.
So this is kind of, I think you have to work a little bit harder than this, and I honestly don't have it in cache, but this is sort of already telling you that there wasn't a small local explanation. Right? We're looking for S to be something like square root. But now you realize that the explanation for what happened, why did we get so many zeros in this block? This could be any in actually a linearly large set, not just a square root n large set.
Yes.
Yeah. So, but you're absolutely right, and it's a good observation. This had better crash, like in a major way, for K-1 partite graphs, and for K-1 colorable graphs.
Okay.
Other questions? Anything from the chat? No? Then let's take a break. So we're back after the break. We had a philosophical discussion during the break. Just so maybe let me say something briefly. Why don't we have a bottleneck node? Why do we need a bottleneck pair, which we're about to define in the next few seconds? We are measuring useful stuff happening. The way we're measuring this when we're talking about clique is we're picking up lots of zeros. And the observation we made is that once you set a single vertex, say V1 here, to 1, you know that you're going to have tons of vertices that are 0. This is not even to scale. Like most of the graph, in some sense, you would expect it to be 0 now, because most vertices are not neighbors of this guy. Okay? But maybe you flip the coin and this was a 0 and you keep on walking and then you get to V2 and you're lucky and you get a 1. Then again, you're going to rule out tons of zeros. Or if that didn't happen and later you get to V3 and there you get a 1, then again, you're going to rule out tons of zeros. So just measuring progress by how many zeros did you pick up is not a good measure, because as soon as you get your first one, you're going to have tons of zeros. So, but what we're measuring is what we want to measure with our bottleneck pair is something slightly more precise. In order for A and B to be useful, I want you to pick up tons of zeros, but then I'm saying also that once you've done that, make sure to hit B. And I've fixed B in advance. And if you think about it, the intuition is that all of these paths, whether I pick up a 1 in V1 or V2 or V3, I would expect the paths to diverge so that they won't be able to hit B.
Yeah.
So the reason why I'm working on a bottleneck pair is I'm saying in order to hit the bottleneck AB, you should first hit A, then you should pick up lots of zeros on the way, and then you should somehow be able to steer your random walk so that you hit B. And now we want to define usefulness in such a careful way that this will be impossible. Does this make any sense?
Yeah, so for k-1 partite graphs, you're saying that because of the structure, we know that V1, V2, and V3 are hitting a bunch of the same vertices.
Yeah, in fact, the structure we had for k-1 partite graph, we had exactly that. We were querying like all the vertices in a particular block. And if we pick them up, for any one we picked up in this block, we knew that we would just do a bunch of queries and then we would clean up and then we would go here, right? After having found the ith clique member, we knew that we had only, we zoomed into one of k choose A possible configurations. So we had, so sort of wildly diverging and then converging again was very easy for k-1 partite graph. Yes, very good point. So we want to argue that in general, that could not possibly happen. Okay, so I fixed some parameters during the break. N to the minus delta. It's not going to be terribly important, but the coin flip bias that we're going to use, I think it's going to enter some of the calculations. It's going to be R times S raised to the power of -1 plus epsilon over 2ek, where e is actually the base of the natural logarithm. It's not terribly important exactly what this is. This is what it is in the paper. We're going to need exactly this value in order to get our calculations to work out. The point is, it's going to be roughly inverse in S to the -1 plus epsilon. That's sort of what you should keep in mind. So this is our coin flip bias. This is the probability with which we're going to pick up a 1. Okay, and then we use some notation for the ith clique index and a branching program node A. Vi0 are all the vertices for which we have said that no, this vertex is not the ith clique member. Vi0 are all V's for which we ruled out V as the ith clique member in beta of A. So the branching program remembers this as A. V1 of A is the vertex, if there is a vertex, it will be only one, such that BA has actually figured out that X, the ith clique member, is V. Okay, just a piece of notation. And now we're ready to define useful, truly useful. I should say everything, all the initial observations 1, 2, 3 that we had about the distribution, they still hold. We haven't changed the distribution. And in particular, any path will rule out the clique axiom, all of this, and it cannot have forgotten the clique axiom that it ruled out. Like all of this is still true. And we're going to use it heavily. Okay, so look at the pair AB of branching program nodes. So capital pi square. Let's say that it's truly useful, as opposed to useful star, but I think from now on I'll only say useful. But if there is an index I such that the following holds. Three conditions. It is not the case. So look at what the branching program remembers. Look at what the branching program remembers at B. Well, it had better not found the ith clique member. That would be like terrible. So it hasn't figured out a vertex that actually is the ith clique member. I is not forgotten at B, and hence not at A, if a path passes through A and B. And here comes the thing that was missing before. Now let's look at VI0B minus VI0A, and let's take a moment to parse what is this notation. These are the number of zeros that you might pick up between A and B, right? Along any path from A to B. Okay. I want this to be RQ neighbor dense. Okay. And now it should already make some sense that if I can get this, then you see now that, well, getting all of those zeros in an RQ neighbor dense set, that's going to require some serious coin flipping. And getting all of those coins zero, that's not going to be terribly likely. Okay, that's where we're headed. Okay. Okay, if we have a useful pair, fix just by notation, let's let I of AB be an index witnessing the usefulness. Okay. And now let me say that a path alpha, you should think of this as an alpha. I mean, these will be sampled according to D, but any path alpha usefully traverses the useful pair AB. If alpha goes through A and then B, so in this order, it sets at most K over T once in the interval from A to B with A included and B excluded. Okay, so a path is useful if it hits A, then it hits B. It doesn't set too many ones in this segment, and yet it rules out apparently an RQ neighbor dense set. Okay, yes?
Sorry, I think I got lost. What's T again?
T is the parameter that we set over here. It's not going to be terribly important.
And like, oh, okay, but semantically, what is it supposed to represent, kind of?
T is the number of waypoints we're going to have. Remember that we took the path and we chopped it up into bits.
Okay.
So like T is the number of chops we're going to make. Yeah. I could have said that. I should have said that. Thanks for asking. Any other questions? So we're at a point now where I can say that you should be like, by the proof we did last time, we are done if I can prove the following. So here comes a lemma 9. This was observation 4 last time. So lemma 9 says that every path alpha in the support of delta, any path alpha sampled according to delta, usefully traverses a useful pair with probability 1. Okay. Except now it's not blindingly obvious why this should be true. We'll have to work a little bit for this, but I claim it's true. Okay. This was like dead easy last time. We got it for free. Now we have to work a bit. Suppose that we get this, and suppose I can prove to you that, and this is where we had the hopeful claim 6 that was very false. But now lemma 10 is going to be true. Just fix a useful pair AB and sample A according to the distribution D that we have still over there, then the probability that alpha usefully traverses this particular fixed pair AB is at most 2 times S raised to the power of minus epsilon r over 2. Okay, and now if we look at how the parameters are set, again, S was basically n or some polynomial in n, R was scaling linearly with k, epsilon is at least positive, so this is going to be n to some constant times k, minus this, okay? So essentially, with probability n to the minus k at most, we hit a particular useful pair. So, but since this happens with probability 1, then I get that, well, the proof had better be, basically 1 over this and then a square root. And this gives us the lower bound. I was not trying to write this down again, like nothing happens, right? I'm just saying that this probability is n to the minus k. How many pairs can I have? Well, at most s squared, where s is the size. So s squared then is at least 1 over this. And the only way that can happen is that if so, the size of the branching program S is n to the big omega of k. And then obviously offline, you have to check that I'm not lying for you, right? But I am not lying. Does this make sense? So basically, I'm telling, my claim is if we can do 9 and 10, then we have deserved our break. Are we happy with this? Good. Let's see how we can do 9. Okay. So we have alpha sampled according to D. Suppose that it ends in the I star clique axiom. I mean, it ends in some clique axiom, so let me just give it a name, right? We also know that alpha sets less than k once, right? Because if it set k once or more, then it would have found a k-clique, and that would be super surprising. So we just split alpha into t pieces. Okay, so here is the branching program. And the path looks something like this. And I'm just going to split it into waypoints again. A0 over here, A1 is maybe here, A2 comes already here, A3 somewhere here, A4 maybe here, and this is A5. So apparently, it seems that T was 5 here. So A1 AT such that in the path between, let me get the indices right, between AJ and AJ plus 1, and just for concreteness, AJ included, AJ plus 1 excluded, we have at most K over T variables set to 1. Okay. I claim we're pretty close to picking up a useful pair. The existence of I would propose I star. That I star would definitely not fee, that I star is not forgotten anywhere along the path, right? And in particular, I never set it to 1 also. And the only problem is, am I sure that somewhere I'm picking up zeros in a dense set? Okay, and the answer is yes, because that's how we set up our definitions. Okay, so we'll just, it has to be true. So let's see how we do this. Well, suppose not. So let us define WJ to be VI star 0 at AJ minus VI star 0 of AJ minus 1. Okay, so this is V1 is the zeros on this stretch, V2 on this stretch, V3, W3 on this stretch, etc. And if one of them is neighbor dense, then we're good. Okay, but what if none of them are? Okay. Suppose no WJ is RQ neighbor dense. Okay, well, that is for every J in T, there exists some bad set RJ that is of size not too large, right? Size at most R, such that when I look at all the common neighbors in RJ, in WJ, and I take their common neighbors, it is unfortunately too small. Yeah. I don't think I'm going to need that, but let's see. But yes, strictly smaller. Okay. Let R be the union on all of these sets. So here is an observation that I will need. Look at, since I never forget anything, right? What can we say about how many zeros, like what is V I star of 0 over here? Everything, right? The whole set. Yeah. Over here, I picked up, I know that there is no vertex in V that is the ith clique. That's why I'm violating that axiom. Okay. Okay, good. Yes, yes. Can I say anything about, am I forgetting anything about along the path? No. So I'm growing monotonically towards picking up all of these. So it's an easy observation that, in fact, I'm going to get that V is a partition W 1, 2 up to T, they partition V. Yes? Do you agree with this? Okay. So now let's look a little bit at this set R. And let's see what common neighbor R has in all of these. Okay, because we have a partition, the size of this set, I might as well sum over all my j's in T. R, right? This is an equality.
Yes.
Okay. Now, I claim the following. Suppose I make this set smaller. What can happen to the size of the common neighbors?
If you make what smaller?
Can only, if I make R smaller, what happens to this quantity? Can only grow, right? Okay, so I claim that this then has to be smaller than n, this should have been a j, sorry, nwj rj, right? I mean, rj is contained in this. Okay, but now I know that this is, yeah, actually I wonder if I let me use the strict inequality then. I don't remember exactly how I set things up. Maybe, yeah, I probably need this. And I was a little bit too relaxed. Okay, but this means, what do I know about the size of these guys?
Yeah, less than Q.
Less than Q, and T of them. Okay. But this is pretty surprising. Now I found a set R. How large is R, by the way?
TR.
Most TR. Yeah. And how many common neighbors does it have in the graph? Less than TQ. But that's pretty surprising because V is TR TQ neighbor density. Gotcha. I told you we just set it up so that this is...
Yeah.
No, but this is sort of saying that yeah. So it can't be. It's sort of along some stretches. You might have gotten a lot of free zeros, but there's one stretch where you didn't, at least. And now this proves lemma 9. This is contradiction. Cannot be. Hence, there is a WJ that is our Q neighbor dense. Obviously, for this RQ neighbor dense W, we're going to use the fact that it's almost neighbor dense for much better parameters, except for this pesky set S. Right? That will give game plan. And that's what we're going to use to get lemma 10. Does this make sense? Let's see. So so what do we want to prove? I'm planning on clearing the board now, I think, or at least clearing the two middle columns. We want to prove now, just for every useful pair that is usefully traversed, that is a highly unlikely event. Okay? Questions while I'm clearing the board, or should I just repeat something again? Or are you just bored to death because I'm going too slowly? Or am I just throwing so many definitions at you that you stopped resisting at this point?
We didn't say anything about how we define these A0s to AT.
Yeah.
Oh, I did. I just chopped them up by the number of ones.
Oh, number one.
I know at most K ones.
Yeah.
So I just, and let's look at how many ones there were. I just chopped them up evenly. Yeah, yes. Thanks. I could have said that more clearly maybe. But yeah. Okay. So now we're just going to prove that it's unlikely. So we fix some notation. So AB is going to be our useful pair, truly useful. Let me write fancy style capital E or E A comma B to be the event that alpha usefully traverses AB. Okay. And in fact, I don't know. Let's see how much energy I have. Maybe I'll just write curly E. And you can, because AD is fixed now. We're gonna have lots of probabilities where all our probabilities are gonna be with respect to the random sampling of the random path. Nothing else. Okay, so AB is fixed. We have no idea about other things. There are lots of dependencies and such, but we do know something about the path. And again, to stress the thing we had last time, this is maybe not the smartest way of picking ones, right? Note that if we're flipping a 1 here and just picking up that 1 will immediately lead to contradiction somewhere else, then you would have said, why don't you, like, you know, fine-tune your probability a bit? Well, the reason why we are not doing it is that independence is so nice. We're going to use independence heavily. Like all the one-coin flips, they don't depend on, we're not looking at, oh, what's your candidate clique? What does the residual graph look like? Does it, you know, should I tune this probability of getting a 1 or not? We're not looking. We're just flipping coins. We have complete independence. And this is really how, like, otherwise I don't know how to do this analysis. Okay? We're fixing something more. We're fixing I star to be this usefully mix of AB. We're fixing W to be the zeros we picked up on the stretch between A and B, if I'm writing this correctly. And we know that this is an RQ dense set, right? Let us also look at the following interesting set. This should be an, hang on. Let me look at V1 of A, which I apparently, which I am defining now. V1 of A, as we noted, this VI1 of A, that's like a very boring set. It's either the empty set or it contains a single member. So, but let me take the union over all the I's. Or all the J's, just in order to avoid contradiction. J goes from 1 to K. V J1 of A. Let me look at this. What is this? This is the candidate clique at the start. Right? This is when I'm entering A, how much do I know? Note that I might have picked up ones, like different ones along different paths, but they are not very useful. The only thing the branching program can use in A is like what it knows along any path to A. And we're going to use that, as I already said, for every V in V1 of A, there is a unique JV such that X V JV is 1. Because it's remembered along all the paths. It can't be that I have picked up different ones along different paths, because then things are forgotten. Is this making sense? So actually this, I can think of this as a set of vertices, but it's also like, once I tell you what the vertices are, they're actually exactly identifying the clique indices also. We said that W is RQ neighbor dense. The graph is clique dense. And since W is RQ neighbor dense and the clique is the graph is clique dense, this tells us by the clique dense property that V is also, and hang on now for parameters, TR or Q prime S mostly neighbor dense. What does this mean? This means that even for sets this large, they have Q prime common neighbors. Any set R that is this large has Q prime common neighbors inside W, except for what? Well, except for this set intersects some bad set S. Let's fix the bad set S. Okay, there exists such a set S. S has size at most S, lowercase s, witnessing the mostly neighbour-denseness. I'm just setting things up so far, just working on the definition of clique-denseness. Okay, how are we doing on time? Okay, let me maybe, so we did some of this last time. We now get a case analysis, and let me see if I'm not sure whether let's see how carefully I do this. Maybe I'll do the easy case quickly and the boring case a little bit faster. Case one is the boring case. We actually did this last time, so maybe I'll just tell you, we have to do the calculations. Maybe I'll do the calculation. The point is, the candidate clique that I picked up at A is already pretty large. And this can make me nervous now, because obviously if your candidate clique is already this large, then we're picking up lots of zeros, right? But honestly, if I have that many ones, how likely is it even, this is a fixed set of ones, right? How many chances do I have? Note that these are, in this, there are unique variables, right? There is a set of exactly these variables. I have to flip all of them and get one for all of them. How likely is this? That's super unlikely, right? Because it's a biased coin flip. So I have to flip this many times with essentially probability S to the -1 plus epsilon. And every time I have to get the right coin flip. Or else I will not hit A by the read once property. Okay, but that means, so basically what we said, maybe just let me write down. So by what I've said so far, if you let me define B1 of A to just be all the variables set to 1 by beta of A. Sorry, so beta 1 of A is just all the variables set to 1. What we argued above is that beta 1 of A is exactly the same size as V1 of A. And I only get one chance per variable to flip it correctly. So now the probability of epsilon, sorry, this is not epsilon, this is the uppercase curly E. So the probability of uppercase curly E in this case is lower bounded by the probability that alpha reaches A in the first place. And the probability of that is upper bounded by picking up these ones. This is not sufficient, but it's a necessary condition. Okay, so this is going to be plugging in the right coin flipping probability RS minus 1 plus epsilon over 2ek raised to the power of beta 1 over A, size of this. And now you just work on this. And this is going to be S to the minus epsilon size of V1 of A, which is the same as this. And this is in turn going to be at most S minus epsilon R over 2. Okay, basically, I'm skipping a few steps, but you got the main idea. We're picking up lots of ones. They're all, note that ones are completely independent coin flips. And so if I have this many ones, it's already very unlikely to hit A. Okay. Are we happy with this? Okay. So then case 2 is that we don't have that many A's, and that we don't have that many ones in A, at most R over 2. Okay, so now for any path alpha, let R of alpha be all the vertices U such that sum x u j is set to 1 in the interval between A and B. And note that if alpha doesn't even pass through A, then we just define this to be the empty set. Okay. By the definition of usefulness, so if alpha is in this good event, then alpha is not allowed to set too many ones. So we know that R of alpha is at most K over T rounded up, just by how we define usefulness. And now the reason we failed, we're right at the point now where we crashed and burned before. Because we had V1 of A was small, but nevertheless, V1 of A together with a few guys here could make us pick up ones so that we got tons of zeros. And we want to argue that that cannot happen. Suppose that it will still happen. Suppose that R alpha is such that suddenly, we pick up a few ones and then just tons of zeros follows in all of V. What can we say about such an R alpha? Well, intuitively, no, it can't be big because we won't pick up many ones, but that is going to be a witness. Like if R alpha is bad, that's going to be a witness that W is not sufficiently neighbor dense. What do we know about R's that show that W are not sufficiently neighbor dense? We know that they have to intersect S in a major way. Okay, so basically we're now going to get a sub-case analysis depending on what's the probability that R alpha intersects S a lot. And we're going to argue, well, if that happens, then we're screwed. But that's going to be unlikely. And if it doesn't happen, then finally we're in the setting where we have lots and lots of unbiased coin flips. All of them are coming up 0, and that's fine for every single coin flip, but there are just too many of them. Not all of them would have come up 0. Should I say that again? So basically, either R alpha is dangerous, but then it intersects S a lot, and S is not too large. So again, we have this, you have to pick up sufficiently many ones in S. We're just going to do a union bound argument and say that this is going to be unlikely. And if R alpha does not pick up sets in the dangerous set S, then we can scale up neighbor denseness, and we're going to have lots of free coin flips that all come up 0. Okay. So let me define fancy style R0. All sets R of size, the right size, at most KT, K over T, and suppose that when you look at R and you take the union of R with V1 of A, and you look at the common neighbors, you get that this is smaller than you would have liked, right? This is the case of if R alpha is in this set, then it's a dangerous R alpha, and we're going to crash. But again, we're arguing that such sets are rare. And otherwise, let's look at R's that have again the right size, but are such that the common neighborhood of R and V1 of A inside W is what we would like. Okay, so any R alpha ends up in either R0 or R1. So we're just doing a case analysis again. Okay, so probability of epsilon is going to be exactly, sorry, this is again not epsilon. Probability of the event, uppercase fancy style E, EAB, even maybe I should write AB to keep myself honest, is the probability of uppercase EAB and R alpha is in R0 plus the probability of the event EAB and R alpha is in R1. So if I can analyze these two guys, and we're done. And now I think I'm clearing the board, and hopefully we'll just remember. And let me maybe these probabilities, let me call this probability P0. Let me call this probability P1. And I'm just going to upper bound both P0 and P1, and then we'll be done. Okay, so R alpha, look at P0 first. So R is in R0. Well, R alpha is at most K over T. And now let's take a very crappy bound that's at most 2K over T, which is equal to, just rewriting this, 2K over T is T half times 4K over T squared, unless I'm messing up. And of course, I'm just shooting for this, because we know by assumption that this is less than R, so we get RT over 2. Okay, just by, where do we have this? I just magically slip this in here. Okay, but that means that if you look at R alpha union V1 of A, what do I know about? Well, we know that this is at most R half, which since T is greater than 1, in particular, it's at most RT half. This is at most RT half. So this union is at most RT, right? And W is apparently not Q prime neighbor dense. Okay, W is not Q prime neighbor dense. Okay, the only explanation is this. So we have apparently that R alpha union V1 of A intersection S, remember that we fixed S. This intersection has to be somewhat large. How large? Has to be size at least R. Well, but how large is this set? At most R half. So R alpha intersection S is at least R half. Is this making sense? Okay, so now we just need to look at what is the probability that R alpha intersection S for a fixed set S is this large. And basically, we are going to need like, okay, so this is going to be just sum up over all choices of XV, JV for V and S. Look at all of these variables of size at least R2. And look at the probability that all chosen XVJVs are set to 1 in alpha. Right? That's what's going to happen. We have to find some choice of at least R2 guys in S, V in S, I know, and some JV. And I have to hit the 1. Okay, so let's see what this is. How many variables are there? So we can be fairly generous with our counting. So we have like size of S times K variables. I need to pick R over 2 of them, right? And then I need to get all the coin flips right. All the coin flips are S minus 1 plus epsilon 2EK. How many coin flips? R over 2. And now we just need to work on this. Am I making sense? I'm just doing a union bound. Like, what is? Look at all the possible X, V, I variables in S. I have to pick R over 2 of them. I have to set them to true. So which one are you setting to true? Well, this is how many ways you can choose them. And then I just look at the probability that all of them are set. And this, just by stupidest of union bounds, it has to be this. And now we just use the math. In fact, here, okay, so using now that, what do we need to use? We're just going to use that n choose k is less equal ne over k raised to the power of k. Not a great bound, but it's good enough in the range we are. And also we know that S has size at most S. And then we do some calculations. And we get S minus epsilon R over 2. We're just, nothing happens. We just massage this using this. Okay? Are we happy with this? Okay, so now look at P1. For P, the probability P1, that's when the path, the ones we picked up are in R1, meaning even looking at the ones we picked up together with the ones we knew at A, we still had a neighbour-denseness. So morally, we should be fine now. Now our flipping argument should finally work. And the claim we're going to make is the following, that any path alpha sampled according to D contributing to the probability P1 sets at least Q prime variables x u I prime to false for u in W as results of coin flips. And now I'm going to argue that Q prime is large enough that when I look at the probability of all of these coin flips being 0, that's going to be good enough. Okay. So let's see how to argue this. We are now okay. So VI star 1 of B is the empty set, and I star is not forgotten at B. How do I know? Well, by definition of usefulness, this holds. So I mean, I'm going to rule out this index. I definitely don't pick up a 1, and also the index is definitely not forgotten. For this reason, the same holds for any C before B. So I'm now looking at, I'm trying to control what happens, like let's C be a vertex somewhere in between A and B. And I claim that for any such C, we also have that we don't have a 1 and I star is not forgotten. And this is just by juggling the definition. Okay, because, well, if I star were forgotten at some C and we continue to B, then forgetfulness was something that accumulated, right? You could never unforget things. Okay. Okay. Okay, so what does this mean? This means also when you look at C and you look at any of the Q prime guys that are common neighbors of all of R alpha and V1, what this says is that we're not getting a forced choice, right? The fact that you're in the common neighborhood means that you're not violating an edge axiom. The fact that you haven't picked up a 1 means you're not violating a functionality axiom. So you're not answering 0 because of reason A. Since I star is not forgotten, you're not answering a 0 because of reason B. And also, for all C that live in between A and B, exclusive, it's not so hard to see that, well, V1 of C is at most V1 of A union R alpha, right? V1 of C, I don't know, you know, I don't know about the ones picked up at B, but suppose I have at most the ones picked up at A, and then just look at all the ones picked up along the path. I mean, this measured the ones picked up only along this path when I reach B. When I have not yet reached B, clearly I have at most these guys. Am I making sense? So I'm saying that looking at V1B union R alpha is like the worst case with respect to ones. Okay. So what I'm saying, so this is the worst case scenario with respect to my candidate clique. If I have free choices with respect to this, then I have free choice. These are the free choices that I have if I'm looking at a vertex at B. And certainly then I have more free choices along the path before. Okay, but that proves the claim then. because this tells me that the Q prime guys that are in the common neighborhood of these guys are definitely in the common neighborhood before on the path. Am I like beating around the bush, or should I say it again? Should I draw like a picture? Basically, what I'm saying is we have A here. Okay, maybe even another. We have A here. A. And then we have the path. We have B here. And here I'm saying, okay, what do I know? Here I have, here, if I walked along this particular path alpha, then I have the ones I knew here. And then I have R of alpha. This is like what I know here. And then I'm saying, well, here is some vertex C along the path. How many ones could I have picked up here? Not more than this, right? Because I'm measuring all of the ones I know here, and then I'm adding in all the ones picked up along this path all the way to B. So, and that means that if some vertex in W is in the common neighborhood of these guys, then it's definitely a common neighborhood back here. And that proves the claim. But then, okay, but then all we need to do is some math. That means that we now say, we now get that, well, the probability that our event happens and that R of alpha is in fancy style R1, that is the probability of alpha getting coin flips x u I star equals 0 for q prime fixed vertices, namely the one in the common neighborhood. Okay, but that is going to be, now we get an equality here. This is 1 minus rs minus 1 plus epsilon divided by 2 ek raised to the power of k prime. Right? This is the probability of getting 0 every time, but I need it 2 prime times. And now it's getting late in the day, nothing happens. Now we just need to plug in parameters. What are we going to use? We're going to use that 1 minus x is not equal. That was a little bit good. 1 minus x is like less equal e to the minus x. If you just use this and do the math, which you have in the notes, like I wrote this out carefully in the notes, and again, boom, you get this. I want to stress that nothing happens. We're just massaging, we're taking this expression, plug in this, and then just work on the exponent and cancel out this. Nothing happens. I could do it, but I'm thinking it's getting late in the day. Okay, but then we're done, because then you just, we got this probability for both cases, so we got 2 times this, and that's exactly what the lemma 10 that we now conveniently erased claimed. Like lemma 10 claimed 2 times this, and we did a case analysis for fancy style R0 and fancy style R1, and in both cases we got this. Assuming, and this was the case analysis for when we did not remember too many ones at A, right? This was already, these were the 2 subcases. In the second case, namely when V1 of A was small, we did not have a large subclique in A. And the case we did before was that, well, if we do have a large subclique in A, then we're not even likely to hit node A in the branching program. Okay, so first we argued that if the subclique, if the candidate clique at A in the branching program is large, then it's very unlikely that a random walk hits that node. If this candidate clique in that node A is not too large, then by neighbor denseness, the only way we can make lots of progress when reaching B is being extremely lucky with our concept. Or being extremely lucky in hitting the dangerous set S. Okay. But this is it. So now I really want to wrap up. Let me try to questions about this. I want to say a few things about open problems. I'm sorry, this took a bit longer than expected.
I do have one question now.
Please go ahead.
About this. It may be because I think I still have to wrap my head around the notion of clique-denseness for a graph, but are we, for whatever parameters you put in there, are we sure that such a graph exists?
We are, the theorem I cheated you on is for the parameters that I fixed and I had on the board at some point, a randomly sampled Erdős graph with exactly the edge density I told you, like n to the -2 times eta over k minus 1, satisfies clique-denseness.
Yes, yeah, I remember that.
But these are calculations.
Yeah.
These are like 3 to 4 pages of careful calculations. Okay, open problems. Well, one, generalize the lower bound to general resolution. Okay. And if you think about it, we used regularity all over the place, but these properties are not regular. Like it might be like if we work hard enough, maybe clique-denseness is enough to get something for general resolution. We just don't know. Like our argument about these picking up ones and zeros were very, very regular, but these like main combinatorial properties of the graph are not regular. The average case would be fantastic. But even worst case would be fine. I mean, worst case would also, it wouldn't be super exciting, but it would be somewhat interesting. It's worth noting that there are 2 papers, one by Massimo Lauria and myself, one by Atserias and Rényi, that do some kind of reduction style arguments to get lower bounds for instance, coloring, which we'll talk about in a few lectures, and also lots of other constraint programming problems. Maybe you could do something like that for clique to somehow, basically, if your proof system is expressive enough to carry out some kind of non-trivial reduction, then you can sometimes get worst case lower bounds in that way. Even that is not known, but it might be doable. Getting like an average case lower bounds probably requires other techniques than reductions because reductions screw up the distribution. Okay. Other question, what about lower bounds for polynomial calculus? And beyond. We have nothing, as far as I know. Like for all we know, you know, if you're looking at a graph, does this graph have a clique of size 1 billion? You fire up your Gröner basis algorithm, you know, maybe it runs in linear time for all we know. Or at least in time linear of the encoding. Of course, that would be super surprising. Why can't we remove that? Another thing, we're heavily using the fact that these are random graphs. And if you think about many proof complexity lower bounds that we have seen and that we will see going forward, argue if you have, sometimes you get random graphs, but typically you have random lower bounds, like the way you would do it for random KCNF formulas, for instance. And the way we did it for Zekin is basically you sample a random graph or you sample a random KCNF formula, and then you represent it as a graph in some way, and then you say, oh, with asymptotically almost surely, your random object has these very precise combinatorial properties, like expansion, for instance. And then you just say, take any object, adversarial or not, that has these properties, and now you get a lower bound. In some sense, I mean, this is what happens here. We're saying, well, any graph that is clique-dense, for this, the lower bound, but this is like an extremely specific definition. The question is, could you say, let G be a sparse enough expander? Can you get this? We don't know. What about G being a Ramsey graph? A Ramsey graph is a graph that doesn't contain neither cliques nor independent sets of size something like 2 log n, I think. Now, if you sample an Erdős random graph in the right regime, then A, it will be a Ramsey graph, and B, it will be clique-dense so that our lower bounds goes through and gives an n to the log n lower bound. But now suppose I just give you a Ramsey graph and ask, can you prove an n to the log n lower bound? And the answer is no, we don't know how to do this. Another thing that you could do is you could generalize the lower bounds from clique to subgraph isomorphism, which is a little bit related to something we talked about in the first lecture. So the clique problem is basically, I give you a fixed pattern graph, namely a clique graph, and I ask you, can you prove that your pattern graph doesn't embed isomorphically into a much larger graph? But what's so unique with a clique? You could say, given any pattern graph H, prove that H doesn't embed isomorphically into my much larger graph, suitably randomly summed. Okay. We talked about that there were monotone circuit lower bounds and bounded depth circuit lower bounds for circuit complexity for clique. So there have been results that take these lower bounds and extend them to general subgraph isomorphism lower bounds. It's a natural question, and I think an interesting question to ask. Can we look at the circuit complexity lower bounds and in the same way take this machine here or something else and get average case lower bounds for subgraph isomorphism? And the final thing I want to say is like about this to generalize the lower bounds to general resolution. The clique problem, you're having a massive number of vertices, and from them you're picking out a few that are your clique members, which is a much smaller set. In some vague sense, the flavor of this graph is fairly similar to weak pigeonhole principles, where you say, I have a ridiculously large number of pigeons, and they're supposed to fit into a ridiculously small number of holes. Can you prove that this is contradictory? And resolution still struggles with this, but these proofs, like Haken proved it for n+1 pigeons and n holes back in 1985, and it took almost 20 years to figure out similar lower bounds for more than n squared pigeons going into n holes. And these lower bounds were also first known for regular resolution. And then with a lot of blood, sweat, and tears, you could lift them from regular resolution to general resolution. So there was a Pitassi and Raz paper that did weak pigeonhole principle lower bounds for regular resolution, and then Raz extended it to general resolution. And it's an interesting, though somewhat vague question. If suppose that you can like read those papers, basically, you read Pitassi, Raz, and then Raz, and you look at the patch from you look at the diff, right? You extract that, and then you apply that diff to our paper, and then you would get a general resolution lower bound. Okay, is something like that doable? I don't know, but I think the clique problem is really nice, and I've tried to point out like a number of ways in which you can take this and get interesting problems. So this is the first, but not the last time in the course where we really run into lots of open problems. And the reason clique formulas are interesting, looking at my cheat sheet, is also because we have talked about bottleneck counting and random restrictions. This is a technique that we know well and we love. It fails for general resolution in cliques. We've talked about interpolation. It's very unclear how to do this for clique formulas. We will talk tomorrow, I think, about the size-width relation Benson-Wigderson, saying, well, if you can just show strong enough with lower bounds, then size lower bounds and length lower bounds follow. But you cannot prove with lower bounds for k-clique. The width for refuting k-clique is k, period. So like we have these wonderful, we have interpolation, we have bottleneck counting, we have the size-width relation, and clique just makes all of these tools crash. So it's an interesting technical challenge that completely breaks the tools we currently have in our proof complexity toolbox. And finally, that brings me to the end of the lecture. Any final questions from your side before we call it a day?
Oh, yeah.
Yes?
About point 2, when you say we know nothing about polynomial calculus, does that mean really nothing? Or like, for example, the k-1 protects upper bound still holds it?
Oh, I mean, the upper bound, anything that you can do in resolution carries over to polynomial calculus if you have dual variables. also, to be fair, I think we do have some exponential lower bounds for very, very large cliques in resolution. That was known, like the beam in Paletto subarval, know that if you have, like, if you sample so dense graph that they almost, but not fully have cliques of size, you know, what was it? I'm blanking now, n to the 5/6 or something like this. Then we have exponentially n lower bounds. I don't think it has been written down, but I think that people in the community kind of sort of know how to do this for polynomial calculus. So for super dense graph and super dense graphs, super large cliques, you can get lower bound, I think, also for polynomial calculus, though to the best of my knowledge, this has not been published. But again, this would be essentially 2 to the k lower bounds and not n to the k lower bounds.
Yep, okay. Thanks.
But thanks for the question. I was a bit imprecise. Yeah, so again, in a very dense clique regime, I think we maybe have something for polynomial calculus. For cutting planes, for instance, I don't think we have anything. For cutting planes, what we do know, we still have interpolation. So the clique coloring formulas that we talked about now 2 lectures ago, we will prove in a future lecture that they're actually hard not only for resolution, but even for cutting planes. But both for clique and coloring, we don't know anything for cutting planes. When you stop the interpolation and you say, okay, here's the graph. Prove a lower bound on proving that this is not colorable or establishing that this doesn't have a k-clique. Then for cutting planes, I don't think we know anything. And for polynomial calculus, again, for clique, we know things in the high range, high density regime. For coloring, we have a much better understanding there. Polynomial calculus almost matches what we have for resolution up to like minor details in the plan. That we'll also talk about in the future. Yeah. Okay, thanks.